In this video, I'm going to be giving a little bit of intuition behind the disk washer method for finding solids of revolution of bounded regions in the plane. So we're going to start our story off with these two curves here. For the record, it's x squared and the square root of x, but it's not important. And I'm going to take this region bounded between them, this one right here. Let's tilt our plane here. Yeah, like there. And I'm going to take this region and I am going to revolve it around the x-axis here. So I'm carving out this volume here. Cool. So this is a three-dimensional shape, and I want to find the volume of this three-dimensional shape. And in order to do that, what I can notice, like before with the disk method and with cross-sections, that I can have a bunch of disks, but in this case, they're disk washers. So notice that they have an outer radius and an inner radius. That outer radius, here if I make things a little bit, there we go. That outer radius goes to the top curve, and that inner radius goes to the bottom curve. And we're subtracting all the area formed by the circle of the inner radius from the circle of the outer radius. And again, we just add up all of the area of these disk washers, adding infinitely many of them together. We start to get something that looks like that original shape that we had. And at infinity, if we add up infinitely many of those areas, or we integrate those areas, we will have the original figure here given by this. And that will give us the volume of this kind of bowl-like shape. Okay, so we're going to start by giving some intuition for why we use the formula we do for the disk washer method. So I have this region here, just like I did before, and I want to revolve this region around the x-axis. So it's going to be like that. And I get this kind of carved out bowl figure here. And I can notice that that solid of revolution here, the one that I showed you in the demonstration at the beginning of the video, is the same as if I were to take the solid of revolution of this red curve around that axis. That would look something like this here. And I subtract the solid of revolution of the lower curve here around the x-axis. I kind of carved that out. And if I overlay these here, you might be able to see that these produce that solid of revolution that I had. So in other words, we want the volume of this outer one subtracted by the volume of the inner one. We'll use that. We want to carve out the volume of the inner solid of revolution. And so we know that the volume of a solid of revolution is given by the integral over the region of pi r squared du, whatever u happens to be, if it's x or y or whatever. That's going to be our, we want this to be our outer function, so I'll use capital R for the longer radius. See, and here we have longer radii here. And we're going to subtract the integral from a to b of pi times little r squared du. Now little r is the radius to the inner curve here. So that motivates our formula for disk washer method. That is the integral from a to b of pi times big R squared minus little r squared d whatever. Okay, so now let's do some problem solving. So we want to find the volume of the solid generated by revolving the region bounded by the square root of x and x squared around the x-axis. Okay, cool. That's kind of what it's the same thing we've been doing since the beginning of the video. Same setup. So we take this here. This is a really rough drawing of x squared. This guy here is the square root of x. And so my outer radius here is going to be my top curve. So this tells me that the square root of x is my big R. And the inner curve is x squared, so that tells me that's going to be my little r. So my volume is going to be given by the integral from a to b, pi times big R, which is the square root of x, minus squared, minus little r squared, which is x squared, dx in this case, because we're integrating across the x-axis. Now for my bounds, they're just going to be the bounds of my region, so I just need to set my two curves equal to each other to find when they're going to intersect. So I will have the square root of x equals x squared, finding my bounds. So squaring both sides, I get that x is equal to x to the fourth. Subtracting x from both sides because I don't want to divide by x because that assumes that x is not 0. Now I can factor out an x and get that 0 is equal to x times x cubed minus 1. And I'll let you verify that this means that x equals 1 and x equals 0. So my bounds are from 0 to 1. Or sorry, yeah, from 0 to 1. So my volume is going to be given by the integral from 0 to 1 of pi times square root of x squared is x squared is x to the fourth, dx. Solving this integral, this is going to be pi times the integral of x is 1/2 x squared minus the integral of x to the fourth, 1/5 x to the fifth, evaluated from 0 to 1. That's going to be pi. When I evaluated at 0, everything zeroes out, so I don't have to worry about it, of 1/2 minus 1/5. Giving these a common denominator here, I get that this is going to be 5 minus 2 over 10, or 3 pi over 10. And that is the volume of the solid of revolution that looks like this here. The one I showed in the intro demonstration there. It has a volume of 3 pi over 10. Okay, moving on. We want to find the volume of the solid of revolution generated by revolving the region bounded by x cubed and x in the first quadrant around the y-axis. Okay, so we're revolving around the y-axis. This is going to be our axis of revolution. And we want x cubed and x in the first quadrant. So this is the region we're talking about here. And we're revolving around the y-axis, so my radii are going to originate at the axis of revolution, at my y-axis. So I need to put my functions in terms of y because my radii are going to be given in terms of y because I need to integrate in terms of y. So what I mean by that is my volume is going to be given by the integral from a to b of pi times big R squared minus little r squared dy. So these guys need to be in terms of y. So I will do x cubed in this color. So y, we write y equals x cubed. I can take the cube root of both sides and x equals the cube root of y. And that is my bigger radius, so that's big R. And then the other curve, y equals x, that's the same as saying x equals y. And that is going to be my little r here. And then to find my bounds, I need to set my two curves equal to each other. We want them in terms of y, so we'll set the y equal to each other. So we have y equals the cube root of y. That means that I have y cubed equals y. So y cubed minus y equals 0. And this will imply that y equals 0 and y equals plus or minus 1. We're in the first quadrant, so we take the positive one. So my volume is going to be given by the integral from 0 to 1 of pi times my big R squared. Big R was cube root of y, so I have y to the 2/3 minus y squared dy. Evaluating this, pi, so 2/3 plus 1 is 5/3. And then that's going to be 3 over 5 y to the 5/3 minus 1/3 y cubed. Evaluated from 0 to 1. Evaluating at 0, it's going to zero everything out, so I only have to worry about 1. So this is going to be 3/5 minus 1/3, which is going to be, giving these a common denominator, 9 minus 5 over 15, which is going to be pi times 4/15. And that is the volume of the solid of revolution that looks like this. There you go. Okay, and that wraps up what I wanted to say about the disk washer method. And if you found this helpful, please consider liking and subscribing. Thanks.